So good evening, everyone. So in the last class, what we left was we were doing this question. So was everyone able to solve this? The last question. So were you able to solve this question? Okay, I don't know why the waiting room got activated.
Good evening, sir.
Good evening, everyone. I was wondering why was no one speaking, and then I found that everybody was waiting in the waiting room. So I don't know what happened to the settings. I have to check. So I hope I'm audible to everyone.
Good evening, sir.
Good evening. Good evening, everyone.
Yes, yes.
So this was the question which I gave you in the last class. So were you able to solve it? If psi1 and psi2 are eigenvectors of an operator A with eigenvalues as half and minus half respectively, then A psi1 plus B psi2, where A and B are complex numbers, is an eigenvector. These are the options. So were you able to solve this question? This was the question given to you.
Sir,
Yes.
there was another question as well, sir.
Okay, tell me.
It was in the other PDF, yesterday's PDF.
Okay, what was the question? Give me the statement.
Just a minute, sir. It was like, which one of the function gives below represents the boundary eigenfunction of an operator d square minus d square by dx square in the region 0 to infinity?
Okay, that was for the gate question. There was a gate question, right?
I think so, sir.
Yeah. So that is the answer is a exponential to the power minus 2x.
Okay, sir. Okay.
Yeah, that is the answer. All right. So okay, so somebody said me the answer is D. Okay, let me begin. So I don't know what happened to this that everybody has to wait outside before they can join.
Oh, yes, sir.
Yeah, so I think there's some change in settings. Let's see. Now this question is very straightforward. You need to now it says that what is the eigenvector, like it says that psi1 and psi2 are eigenvectors of an operator A cap with eigenvalues half and minus half respectively. Then A psi1 B psi2 is an eigenvector of so let's see what happens when we operate. So let's see what happens when we operate A operating on A psi1 B psi2. All right, so now A so if you operate this, what will you get? This is A. Now this is A psi1 plus B. Now this will operate like this. Okay, so this will not affect the complex numbers. All right, so this is A. Now if you operate this, so in this case, you will get this is A. Now this operating, so it will give you half psi1 minus this will give you half B psi2. Okay, So now one can see that this is not an eigenvector of A. It's clear that it's not an eigenvector of A because this function clearly changes. It becomes A psi 1 minus B psi 2. All right. Now in this case, if I operate it twice, if I operate it twice on this function, all right. So what will you get? Now, once we have already obtained the operation is done. Now we'll like take this result itself and write it here. So this is A psi 1 minus B psi 2. All right. Now, when you operate this again, so what you get is A operating on psi 1 will give you half psi 1, and then B, this operating on this, you'll get B, and there will be minus 1 by 2 psi 2. And then when you rearrange this thing, you'll get this is A psi 1 plus B psi 2. Now this is you're getting back the function again. You're getting back the function. So this is an eigenvalue equation, and where the lambda is this, where the lambda is 1 by 4. Okay, so the correct option is that the, it's an eigenvector of A square with an eigenvalue 1 by 4. All right, so the correct option is D. All right, so moving on.
Okay, sir.
Now, yeah, so moving on this thing that unitary operator. Next is unitary operator. Now, these lectures are also available in on YouTube channel. All right, Paper Money. If you miss these lectures, live lectures, you can always see this in on YouTube. But be prepared before coming for the next lecture. Please make sure that you see the previous lectures. All right. So, and operator U, an operator U is said to be unitary if it's said to be unitary if U dagger U cap is equal to identity. Okay, if you have this relation where U dagger U cap is identity, or you can write like this: U dagger, and this is equal to U inverse. All right. So this is how you can write a unitary operator. Now, there's a question. Let me see if I have it with me right now. So this is a question on the unitary operator. Is it available with me right now? Okay, I think I had somehow remember it. Okay, I'll come to that when I get that question. No, I don't have it with me right now. So the question was somewhat like if this is an unitary operator, which kind of operator it is. So it's not. I'm not getting it right now. So what I'll do is if I can recall that question, then I'll write it down. So moving on to the next concept. Okay, so example, I remember the example, but not the exact question. This was the if you have been given this operator, which is I H cap. All right. So this is the operator given to you. Now, tell me whether it's a unitary operator or not. Okay. is this an unitary
Yes,
operator
yes.
or not? So if you operate this, if you take a dagger, so whenever you take a dagger over an operator, so it conjugates the function and daggers the puts a dagger on the operators. So in this case, this will turn to minus iota, and this is plus. Now, and Hamiltonian operator is always Hermitian. Okay, Hamiltonian operator is always Hermitian. So you can write like this, and then when you see this, that if you take this operator and take its dagger, okay, and you multiply them both, so this will be minus I h cut, and then you'll have on this side minus I h cut. So this will give you identity, right? This is basically e to power 0, which is an identity operator, right? So this was a question that whether what kind of operator is it. Now the next thing is we'll learn about the expectation value or the mean value. Expectation value, mean or average value. Okay, this is mean or average. In quantum mechanics, it's mentioned as expectation value. So this is one of the most important things you'll be asked in a question related to quantum mechanics at your level. So the expectation value is associated with an operator. So expectation value is expectation value of an operator a cap with respect to a wave function with respect to a wave function, all right, is defined as it's given like this, that a, now this is enclosed in two angular brackets. We had already discussed this notation when we discussed probability. So this is defined as this, divided by, now if the wave function is not normalized, then we have to divide by this factor. All right, now this was in integral notation. This is an integral notation. We'll write using Dirac notation as this. So this is the Dirac notation for whatever we have written in integral notation. All right, now in this case we have assumed that the psi is not normalized. Psi is not normalized. Psi is not normalized. All right, so in this case,
So that is why we have to divide the term now.
yes, so that is why we are dividing. Okay, if it's already normalized, if psi is already given to be normalized, or you have already normalized it, so in that case you can just simply write, if psi is already normalized, psi is normalized, which is this, the normal, it follows the normalization condition, which is psi star psi dx is equal to 1. Now this is the integral over all space. Now this depends on the region given to you, but let's in general write it like this. So if this is true, then you can write the expectation value of a with respect to a wave function, normalized wave function, as this. And simply write like this: a star a psi dx is equal to psi a cap psi. Right. Okay, so this is what you want to if you want to remember this thing, that how it's defined. Now normalization condition in Dirac notation. Okay, let's see how does it look like.
Hello,
Normalization
sir.
condition in Dirac notation. Normalization condition in Dirac notation.
Hello, sir.
Yes.
Sir, whatever you written above, average of a hat is equals to something. This is a Dirac notation, right, sir?
Which one? This one. This
Yes,
notation.
sir. Yes, sir.
Yes, this is Dirac notation. All
Okay.
right.
Okay,
So
sir.
actually, this is read like this. You'll read it like this. That this is if you want to read this thing, you'll read it like this. That one thing you can say that this is the expectation value with respect to psi, or you can read it like this. That this is bra vector a cap ket vector. Okay, this is how you read it. All right, A is being sandwiched between bra vector and a ket vector.
Okay. Okay.
All right.
Okay, sir.
So normalization condition in Dirac notation. So it's written like this, that psi. Now this is famously called the inner product. Okay, so this thing, psi and psi. All right. Now this is where the bracket name came from. Now this is the whole thing is called the bracket. So this part is becomes bra, and c is kept smaller, like it's not put in the name. So this is the bra, this is the ket. So bracket, from bracket it's derived this name. All right. So this product is basically called the inner product or scalar product. Okay, now this notation in integral form is like this. In integral form, this same thing can be written like this. Okay, so this is the inner product in integral form. This is the inner product in integral form. All right. So this is the same as this. Both of these are same statements. All right. This is also normalization condition. This is also normalization condition. This is in integral form. This is in bracket and the Dirac notation. All right. So need to remember this thing. All right. Now the orthogonality condition. Orthogonality condition in Dirac notation. It looks like this. Orthogonality condition. Okay, in Dirac notation. All right. So this is written like this. We know that it was written like this, that psi m star a, sorry, not a, psi n dx was this was 0, right, for m not equal to n. Now in Dirac notation it's written like this. This was the integral notation. In Dirac notation it is written like this: psi m psi n is equal to 0. All right, equal to 0. Now this is m for m not equal to n. Now this is the orthogonality condition. Orthogonality condition in Dirac notation. All right. Now this is also written like this in orthonormality condition. Let's see, the orthonormality condition looks like this: psi m psi n. Now this is equal to 0 if m not equal to n, and 1 if m is equal to n. So see, orthonormality is made up of two words. Orthonormality is made up of two words. One is the orthogonality and another is the normalization. So this comes from the orthogonality. orthogonality, and this is the normalization condition. Okay, so if both of them holds, orthogonality as well as normalization condition, in that case we say that this is this is the orthonormality condition. This condition, the whole thing, this is the orthonormality condition. Orthonormality condition, and this is very important if you want to write down in a superposition state. All right, so in this case, this is the orthonormality condition, and we, in short, we can write like this. We can write psi m psi n is equal to delta mn. Okay, I think some of them are not able to like join this lecture because there was some waiting room issue. I'll check for the next meeting. I don't think I can
Sir,
resolve it right now.
sir,
Yes.
if cat psi and brass ion is equal to -1, if then it could be orthonormal.
What if you're saying if
Instead of
psi n is equal to,
-1.
no, this will never give you a -1. This will never give a negative quantity. All right. This will never give you a negative quantity. Okay, I've never come across this situation. I don't know if it's valid for in general, but this quantity is a positive. This will give you a positive number. All right. So now see, this will you can see from this only that there are two options possible, one or a 0 or 1. Okay, now 1 I say because it could be a finite number, then you have to normalize it. I'm talking about that when psi is it's not it's normalized when psi m and this only, then only you'll get a 1 if both are equal. If m and n means if you're having same psi, if you're having same psi and doing this operation, then you will get 1 if the psi is normalized. All right, otherwise 0. So how can you think of a -1 here when there are only two options possible? All right, either it is orthogonal to some other wave functions given to you, or it's say if the same if it's the same wave function, that it will if it's normalized, then it will give you 1. Okay, or some non-zero value, but it won't be negative. All right. So now if you want to write down the expectation value of a position operator, expectation value of position operator, okay, which is given by this x cap in angular brackets. Now assuming that psi is normalized, now this answer to this question is assuming that psi is normalized. Okay, if psi is said to be normalized, then we can write like this. Now this is minus infinity to plus infinity psi star x cap psi dx is equal to psi x cap psi. All right, so this psi is all for function of x and t. All right, so this is how you can write down. Now we do not know the wave functions, we cannot proceed further. What will happen to this quantity? Okay, it depends on what is the wave function given to us. Now we can note this, that how it's interpreted, how this expectation value is interpreted in quantum mechanics. So this now this expectation value is interpreted as the average value. Now you can write down this is interpreted as the average value of x, okay, that we would expect to obtain from a large number of measurements. So it's like you have several systems, you have several, say 100 copies of the same system, and you have 100 students aligned with each of the systems, and everybody is making some measurement, everybody is making the measurement of position of the particle in the system. So everybody is getting some result, okay, somebody is getting 5, somebody is getting 5.15, somebody is getting 5.6. So there are various range of x's you get, and then you take the average of it. All right, it's like that. So this is the interpretation is like that. You take the average of all these quantities. Now it is also thought of like alternatively natively, okay, it could be viewed as the average value of position for a large number of particles which are described by the same wave function, So these are the two interpretations of this expectation value of the operator. All right. So this quantum mechanics is always open to interpretations. There are several interpretations. You just have to pick one and stick to it. All right. So in this case, this is the interpretation of the expectation value of an operator. Now, expectation value of a momentum operator. Expectation value of momentum operator. All right.
Sir?
Yes.
Sir, if the positions of the different particles are the different, then how can those particles be described by the same wave function?
See, the thing is, it's not like the particle. It can be described by the now. It cannot be very different. If I say that there are 100 copies of the same system, all right. So it cannot be very different from the, like, everybody will have a same wave function. All right, it's defined in that way. Like when we start when we create such a system, we try to create identical copies, like an ensemble. Okay, so in that case it will be slightly different, like, because see, the measurements in quantum mechanics is highly probabilistic in nature. All right, now it could the wave function, when we say the wave function is same, it could mean that the energy states are same. All right, so energy states are same. So in that case, the position of the wave function could be slightly different in the form, but it will represent the same energy state. All right, it will represent the same energy state. It might be possible that there is some perturbation or something like that in the wave functions. So that could create a distribution of positions of a particle. All right, it won't be the exact position. Okay.
Yes, sir. Okay.
So expectation value of momentum operator. So this is given by this px is equal to minus. So whenever I say we create an identical wave function, it means that it is of the same energy eigenstate. All right, it has the same energy. And when we do the waveform, we plot the wave functions in 1D potential, then it will become much more, you'll be able to find out what it is. Now we do not have any idea about what the form of the wave function is, so it's difficult to like give you a direct example. So once we do the 1D potential, we'll understand that what it means to have identical copies of the same system. All right. So when we can write like this, if you take the expectation value of momentum operator, we can write like this. Okay, psi star, and there is a px, which is the momentum operator, which is sandwiched between these two wave functions. All right, this is how it's defined. Now in this case, we can write like this: psi star xt. All right, this is minus I h cut, is d dx. All right, psi xt dx. All right, now the expectation value of, it's also written like this, that if you want to find out the expectation value of some operator, it can be written like this, that expectation value of an operator a cap is simply its eigenvalue. It's simply its eigenvalue. All right, so if we write down a psi is equal to, now we can write like this: if small a is the eigenvalue of this operator with respect to this wave function, then we can write like this. And if you define the expectation value like this, that is psi a cap psi divided by psi star psi is equal to, this is psi, and we have psi and psi, inner product of psi and psi. These two quantities will be equal, because see, this will operate on psi, we'll get a psi, small a psi. Now a is a scalar quantity, it will come outside the inner product. So this is also inner product, this is also inner product. These two will have same answer, whatever it is, one, it could be two, whatever it is. But now this two can be cancelled out, and we'll get a. So we can see that if a is the eigenvalue of the operator a with respect to a wave function, then the expectation value of a is basically equal to its eigenvalue. All right. Now if we have been given this thing, let's take an example. Now if I give you the psi is equal to e to power I kx, now this is a wave function related to the free particle. All right, so this is the wave function of free particle, wave function of free particle. All right, now the momentum, now how can you find out the momentum of this particle? Find the momentum of the particle. All right, find the momentum of the particle. How will you do it?
So we have to apply the momentum operator.
Yeah, you apply the momentum operator on psi. So you have px, you operate on psi, which is minus I h cut, derivative with respect to x, and you have this one is psi e to power I kx. So if you, when you apply this, you'll get iota, and iota will become -1, and then there is minus sign, this is +1, and we'll be left with h cut k e to power I kx. Okay, so which is equal to h cross k psi. All right, this is what you'll get. So this is the eigenvalue. This is the eigenvalue. Lambda is equal to h cut k, which is the which is also the expectation value of the momentum operator. Okay, in this wave with respect to this wave function. All right.
Okay, sir.
Now, so measured values of so the measured value we can write like this: the note, the measurement of momentum in this state gives us the measurement of momentum in state psi is equal to e to the power I kx is h cross k. Okay, this is h cross k. Now next is the normalization condition in superposition state. Now how do we write down the normalization condition in superposition state? Now so far we have been discussing about a pure state. So how can we write down the normalization condition? Okay, normalization condition in superposition state. All right. Now you can write a superposition state like this: psi is c1 phi 1 plus c2 phi 2. All right. So this is how it's written: psi is equal to c1 phi 1 plus c2 phi 2. And here we can write on this state like this in terms of phi 1 and phi 2 only because phi 1 and phi 2 are orthonormal. All right. So then only we can write this wave function. All right. Now this thing that this means that phi 1 and phi 2, if we write like this, if you do this inner product, it will give you 0. And if you do inner product, which is phi 1 and phi 1, it will give you 1. And if you do inner product, phi 2 and phi 2, you will get 1. Okay, so this is what we mean by orthonormality, orthonormal. Okay, then if this is true, if this holds true, then only you can write like this. The same thing where if you write a vector, you try to write a vector, this is ax I cap, ay j cap plus az k cap. So you can write like this only because I and I, this is 1, I and j, this is 0, I and k is 0. All right, this is why you can write like this. Okay, otherwise you won't be able to write this vector in this format. All right, so orthonormality condition is very important in this case. Now what is the what is the normalization condition look like? Now in this case we can write psi and psi should be 1. This is how we write like this. Now if I want to write down psi, this thing, see, we know what is the ket psi. We want to find out bra psi. So bra psi can be obtained by taking a dagger over this thing, over the ket psi, which is, you can write like this: c1 is phi 1 plus c2 phi 2. All right, if you take a dagger, like this, so this will give you what? This will, now this dagger will operate on these quantities. So this is c1 star. Now if we have a dagger on phi 1 ket, it will become bra phi 1, and then we have, this is c2 will become c2 star, and this will be phi 2. All right, so this is what you will get. Now when you write like this, when you take a dot product with or inner product, you write like this. All right, now this thing is writing two things together. Okay, so this one is this part, which is phi 1 plus c2 star phi 2. All right, so this is the bra psi, and the ket psi is this. Okay, so you can simply multiply them right now. So when you take this multiplication, now this term is multiplied by this term. Okay, and then this term is multiplied by this term, and then similarly this term is multiplied by this, and then again this term is multiplied by this. All right, so this is how it's distributed. So this looks like a simple multiplication. So this will be c1 star c1. It will give you phi 1 inner product with phi 1. Next term is c1 c2, and this is phi 1 inner product with phi 2. Okay, similarly you can go on writing the terms. So this is c2 c1 phi 2 phi 1, plus C2 star C2 phi 2 and phi 2. All right, so you can write like this. So this is basically this term is what? This is z star z. So this is C1 mod square. All right, now this is 1. Now the other terms, this is 0. This is 0 because of the orthogonality condition. And then this is C2 mod square into 1. So basically what we arrive is a C1 mod square plus C2 mod square. All right, this is the result for a. Now this is if you can say that this statement is for this is there are two states available. So this is a two-level quantum system. Two-level quantum system. All right, so there are two states available. So this is two-level quantum system. Either it's psi1 or psi2. All right, so this is what you get from this expression. So if when you write the superposition state, the expectation sorry, the normalization condition comes out to be C1 mod square plus C2 mod square is equal to 1. Now you can see from this thing that C1 mod square is plus C2 mod square is equal to 1. All right, so this is the normalization condition for two-level quantum system. Okay, this should hold if this the psi1 and psi2 are the probability amplitudes of the corresponding psi1 and psi2 states. So this is the normalization condition for two-level normalization condition for two-level quantum system. All right. Now, in general, if we have a big superposition state with containing n states, okay. So in general, if we have this situation that in general, if we have psi is equal to which is C1 phi 1 plus C2 phi 2 plus C3 phi 3. All right. Now this goes on, and we are considering that all the phi 1s like phi I and phi j are all orthonormal. Okay, this condition is a must. Okay, then if I write like this, psi, the normalization condition for this state, we can write like this. Now this will become C1 no wait, so C1 mod square plus C2 mod square. Okay, and similarly C3 mod square, it will go on for say Cn mod square. Now this can be written as summation I going from 1 to n, okay, and Ci mod square. This is equal to 1. So this is the normalization condition for a superposition state. Now this CI's are what? CI's are the probability amplitude. Is Ci is probability amplitude corresponding to the ith state. Okay, all right. Now in this case, if we have Ci mod square, what does it mean? Ci mod square is the probability of finding the particle in the ith state. All right, so these are the two things you need to remember from here. Now just think of it like this, that if in vectors, let's take an example. If in vectors we do this, say we have this state which is a written by a 2i cap plus 3j cap plus 4k cap. All right. Now, if I want you to find the component, of I cap, okay, in A. So how will you find out? If I tell you that I want you to find out what is the component of I cap in A vector. So what will you do?
A dot I cap.
E dot
Yeah.
I.
So you just take a I cap or A dot I, so whatever it is, both ways it's same. So you take this product and you get 2, right? Now this is what we do in this thing also. If I want to find out want to find out the probability that the particle is in phi 1 state. All right. So in this case, say if the state is given to me like this, C1 phi 1 plus C2 phi 2. All right. So in this case, if I do inner product, this is also inner product, right? So if I do inner product of that state which we want the particle to find the probability in, so in this case, if I do a like the inner product like this, so what will you get? This will be phi 1 plus C2. This will be phi 1 and phi 2. Now this will become 1, so we'll have C1, and this will become 0. Now this is 0, this is 1. All right, so we get C1. All right, now if you want to find the probability, then we just want this thing. If you want to find the probability of finding the particle, probability of finding the particle in the ith state, in the phi 1 state. So it's simply C1 mod square. Or we can write like this. If you want to find out this thing, that this will be phi 1 inner product with psi whole square. Now this will give us, this quantity will give us C1, and then we take a C1 mod square, will give you the probability of finding the particle in the phi 1 state. All right. Now similarly, we can write this in general, that probability. Now if we have a superposition of state which consists of many states, sorry, so probability of finding the particle in probability of finding the particle in ith state, all right. So yeah, so probability of finding the particle in ith state will be given by mod phi I, okay, and then we have psi, inner product with psi. Now this is a mod square, this will be Ci mod square. Okay, this is how we write this. Now
सर
yes, tell me.
सर थोड़ा सा ऊपर जाइए जहाँ पे मतलब स्टार्ट हुआ है हल्का सा, हाँ बस। सर इसमें 1 और 2 में डिफरेंस क्या हुआ? प्रोबेबिलिटी एम्पलीट्यूड होगा ना पहला वाला जहाँ पे सिर्फ C1 आया है,
ये वाला? हाँ,
हाँ।
this is the probability amplitude actually. No, okay, so this is the probability amplitude. Actually I wanted it to be the whole section, so I wrote it earlier.
Okay.
So this is a probability amplitude, of course, but I wanted to find this thing, so I already, okay, I wrote it twice, so okay, so fine, this is the amplitude.
Okay,
all right. Now let's do an example. Okay, let's do a simple example. You have been given this state psi, and this is given to be phi 1 and phi 2. All right, and it's also given that like this is orthonormality condition is given to be true for phi's. All right, so this is the two things given to you, and find out whether the psi is normalized or not, and if it's normalized, what is the normalization condition, normalization factor, okay, for this psi. So let's assume that the normalized psi looks like this. Now you can check, if you check this, you'll find that if you do what is the check? How will you check whether it's normalized or not in this superposition state? Just add Ci mod square. Okay, Ci mod square in this case. So this will give you C1 mod square plus C2 mod square. Okay, so this is basically, this is 1, this is 1. So in both the cases, this is, both are 1, so this is 2. So this is not normalized, this is not equal to 1. Okay, so not normalized, the psi is not normalized, the given psi is not normalized, given psi is not normalized. All right, given psi is not normalized. So in this case, we have to normalize this. So how will you normalize it? You can simply normalize like this. Psi is equal to, let's say, the normalized psi. We know that any wave function can be, which is acceptable, can be normalized, okay, by multiplying an appropriate factor. So in this case, let's say that a is the appropriate factor or the normalization factor. So if we write like this, now if we apply the normalization condition, so the normalization condition is this normalization condition. All right, so this is summation Ci mod square equal to 1, which is C1 mod square plus C2 mod square equal to 1. All right, so if I take this c's here, so this is basically a square plus a square is equal to 1. Now this will give me, if I write like this, so this will give me 2a square equal to 1, and which is a is equal to 1 by root 2. All right, now if I write down this thing, psi is equal to 1 by root 2 phi 1 plus 1 by root 2 phi 2. Now you could have directly written this down. If you want, you can directly write this formula. If you have this state that this is C, now this is phi 1 and phi 2, B phi 2. Okay, now if you want to write the normalized psi, now if you want to write the normalized psi directly, so you can write like this, that a divided by, now this is root over a square plus b square. Now this, if this is a this thing is a complex number, this should be written like this, a mod square plus b mod square. Okay, then b, this can be written as root over a mod square plus b mod square. Okay, this is phi 2. So you can directly write this, write like this. And if you have several of them, like if you want, if you have not just 2 states, you have more than 2 states, so in that case you can just simply write like this. If in general if you have a state which is made up of, say, C1 phi 1 plus C2 phi 2, okay, and so on, Cn phi n. All right, in this case, if you want to write the normalized psi, okay, so in that case you can write like this. Now I'll take the whole factor common. Now I can multiply by this Ci mod square root over, and this is written as C1 phi 1 plus C2 phi 2, okay, and so on, Cn phi n. All right, so for each of them you can write like this. You can divide this factor to with all to for all the case, all the amplitudes, you'll get the normalized psi. All right, so now this statement is, this factor is basically what this is basically. If you want to expand this factor, this looks like this, C1 mod square, and you have C2 mod square, and then Cn mod square. So this is the fact, this is the whole factor. Okay, so you don't need to remember this formula. Now if I give you this question, that example psi is given to be 3 phi 1 and 4 iota phi 2. Okay, and where phi's are normalized, sorry, orthonormal, delta ij. Okay, so tell me what will be the normalized psi? So you can do it this way also. You can take this, assume that this is a factor is there which we multiply to make it normalized. Okay, so in that case this is 4i a phi 2. All right, now if we write down the normalization condition, so the normalization condition becomes 3a mod square plus 4 iota a mod square is equal to 1. Now, if you solve this, what do you get? This is a mod square. This is 9 plus 16, okay, equal to 1, which is a you get to be uh, this is how much? This is this is 9 plus 16, so this is 25, right? So well, this will become 1 by 5. Now, if we multiply this thing, so finally the normalized psi comes out to be this. The normalized psi becomes, this psi is basically 3 by 5 phi 1 plus 4 iota by 5 phi 2. All right, so this is what you get as a final normalized psi. This is normalized. All right, so let's see a question, or let's say that you have this question, that you have a wave function. Now you have been given a wave function which is c1 alpha plus 2 beta and plus 1 plus iota, which is gamma state. Okay, so this is the wave function given to you where alpha, beta, gamma are orthonormal to each other. So find out what are the values of what is the value of c1? What is the value of c1? If psi1, if psi is normalized, if psi is normalized, then find c1. All right, so can you find it out?
Yes, sir.
All right, so just do this as a homework and we'll do more problems in the next class. All right, so I'll stop here for today, and I'll send a survey form for the time slot so that you can choose appropriate time and we can have a common time slot which is suitable for everyone. All right, so thank you for watching and have a great day. All right,
Thank you, sir.
Thank you, sir.
okay.
Take care.
Take care. Bye.
Thank you, sir.
Yeah, take care.